Okay, we're going to continue and talk about how to evaluate limits algebraically. There are several different ways to evaluate limits algebraically, and many of them coincide with what the function looks like and what it is. The first off is we can use or solve it to find a limit algebraically if we use direct substitution. All right, direct substitution. Direct substitution only occurs if you have a continuous function at C. All right, only works when there is a continuous, or there is continuity, I should say. Continuity at C. All right. So for example, when you take the limit as x approaches C, if there's continuity, that means that the limit will actually equal the value of the function. Okay, so the limit actually equals a value of the function. That's where we can use direct substitution. Those are what we refer to as easy limits. Now, if direct substitution doesn't work, that means we get into an area where we take a limit and we notice that the limit as x approaches C, all right, for the function doesn't equal the actual value. Now, when you notice that it doesn't equal the actual value, there are two instances where we look for. Is that if we plug that in and we actually get 0 over 0. 0 over 0 is what we call indeterminate form. When you plug in a value and you try to use direct substitution, you realize that it doesn't give you a value. It gets you an undefined value, 0 over 0. We get indeterminate form. Now, when you get indeterminate form, there are several different methods to find a limit. One method, what we can do, is a dividing out. I'm going to use a different color here. We can use factoring or dividing out. Or we can use rationalization. Another common one, that would be a fourth one, would be common denominator. Now, in all three of these instances, in order to solve this, the key thing is we just simply need to simplify the expression, or simplify the function. And we're going to go through some examples to show how this would work. Okay, so going through some examples, let's check these out. We're going to just do a few of them, and I'm going to do that. And what we have right here is, in order to solve these, we're going to first always look at and find out if we can use direct substitution. So to do direct substitution, we're going to take the limit as x approaches -1/2, and we have 3x. So we actually are doing this by taking this, and I don't know why I'm rewriting this, but we're going to take this value and actually plug it in. And we're going to find what the value is. We're going to find out, is it continuous? So direct substitution, we can call it ds, to see if it's continuous. Check for continuity. At C. So we're going to just simply take 3, plug in -1/2 squared, and then we're going to take 2, plug in -1/2, that's 1, and do we get a value? Well, in this problem, put this down here. Oops, sorry. Well, it appears we do get a value. This one we get 3/4. Right here, what we have is, it appears to be -1 minus 1, which is -2. So 3/4 times -2. And what we have then is cancel, 2, -3/2. So it is continuous. We get a value. And our limit is going to actually equal that value, which is actually limit, which actually equals f of -1/2. Of course, assuming that is f. All right. That's our answer. Now, in all these are all used with direct substitution, okay, or most of them. If we try example right here, example number 3. In example number 3, we try direct substitution by plugging in the value. So what we have then is either 0, cosine of 0. And what we have is 1 times cosine of 0, which happens to be 1 as well. So our answer is 1. That's our limit. It just so happens to equal f of 0. All right, but that is our limit that we're finding. We can apply that to all of them. All right, but sometimes when we come to problems like this one, we plug in the value, and we realize when we plug in 0, we have 0 and before 4 minus 4. Then we plug in 0 again, and we have 0, and we realize we get 0 over 0. Well, now we've come and noticed that we have indeterminate form. Dun, 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 dun. Form. Okay, and I didn't spell that right. Apologize. Indeterminate form. Okay, there we go. All right, right there. We have 0, 0. So from here, what we need to do is we actually need to simplify this expression. Now, to do this, one way to simplify this is, well, factor it out or divide it out. So to simplify this, I'm just going to simply simplify this right here and see what happens. So when we have this, I'm fill it through. We have 4 plus 4x plus x squared minus 4 over x. Notice that these cancel out, and we have 4x plus x squared all over x. Once we take this, I can simplify a little bit farther, and we're going to take and factor out x, and we have 4 plus x over x. This cancels out, and now once we cancel out, we end up with a simplified expression. We just eliminated, because when we get indeterminate form, we actually have a hole in our graph because it's undefined. All right, but what we have right here, the limit as x approaches 0, once we have that, we plug that back in there, use direct substitution again, and we end up having 4 as our value. All right, so this is just one example or a few examples of how we can do this. I'm going to add another tutorial on doing some more further. But the key thing in kind of review is that when we want to find limits algebraically, we always want to test to see if it's continuous or if there's continuity first by using direct substitution. If we use direct substitution, we identify indeterminate form because it's discontinuous there. We want to simplify the function, okay, or simplify the expression by factoring, rationalizing, common denominator, or a bunch of other ones. We'll do some more of those in the next tutorial.